Hey guys, just doing a quick video on the least squares regression line. So this is one of the big lessons of the topic. So unfortunately, because of the lockdown, it's going to be online. But this is an important part of the topic because you're going to do it repeatedly and you should try to get fast at it. So far we've drawn a line of best fit by eye, but clearly from the trial and error nature of drawing it, like you're pivoting the ruler around the mean point, it's not very mathematical at all, okay? So the preferred method of drawing a line of best fit is actually by drawing this least squares regression line on your calculator. And that is the line that your calculator actually finds when you do a for lin reg on data that you've entered into stat edit. So the calculator actually tries to find a straight line that is as close as possible to all of the data points in your data at the same time. So that's why it's called a line of best fit. But the formal name for it is the least squares regression line. Now just remember that we're only doing this line, we're only fitting a line to the data if r squared, the coefficient of determination, is 0.7. It's only strong enough when it's 0.7. Okay? So what are the steps? You need to enter your X and Y data into stat edit. You need to press stat and go to the right to get the calculator menu and select for lin reg. Tell it what list your X and Y data are in by pressing L1 and L2, or second number 1 and second number 2, and then calculate. And this screen appears. Now, hopefully this is familiar to you because we hammered this in the topic, the second topic of the year. This looks like Y is equal to mx plus c, where m is the slope and c is the y-intercept. But now it is a and b. So the screen appears and it tells you what the value of a is. It tells you what the slope is. The slope of the least squares regression line. And the b tells you the y-intercept of the least squares regression line. Alright, so it tells you all of the elements that you need to be able to actually draw the line equation like we did in topic 2. And so as before, as we've already stated, r squared and r squared is the coefficient of determination. You're only doing this if r squared is greater than 0.7, and also r is the Pearson's correlation coefficient. The next step is you shouldn't leave the equation as y is equal to ax plus b. Really, you need to write your equation in terms of the question. So you remember in the question, the y is going to represent something. So it might be the distance. So you write distance instead of y. And the x is representative of the independent variable. So instead of writing x, you would write age, for example. Like the example that we've been hammering, which was the distance thrown of a discus and the age, you would write those instead of leaving it as variables. And so to draw the least squares regression line, you need to choose 2 points. You need to choose 2 points to be able to draw a line. Our next door neighbours are very noisy. I doubt that's going to help, but anything will do. So remember in the previous topic, you can only draw a line with 2 points. So you need to substitute an x value that's close to the left side of your scatter plot into the equation. You need to substitute an x value that's close to the right side of your scatter plot and solve the equation with these 2 different values of x to get 2 different y values. And these pairs of x and y are points that you can plot on your scatter plot to draw the line of best fit, which in this case is the least squares regression line because you're not just trying to fit it by random, you're actually using algebra to draw it. So let's do an example. The following data shows the distance a discus was thrown by people of various ages, so the same example as we've done previously. I've pre-put the data in, so you don't need to listen to me putting data in. I've also plotted the point, so the scatter plot of the data has been drawn. But this is what's new. Use technology to find the least squares regression line and draw it. So I'm going to do B up here. So I've put the data in into stat edit. I'll scroll over to calc, select for lin reg, tell it where my data is. And now it spits out y equals ax plus b A is equal to 3.2895 to 4 decimal points. B is equal to negative 20.3421 to 4 decimal points. Then it says R squared is 0.8414, so it's plenty strong. It's not the strongest, but it's strong. And then R is 0.9173 to 4 decimal points. So now I can actually write the equation in terms of the question. Its distance in meters is equal to 3.2895 times by x, which was representing age, minus 20.3421. That is the equation of the least squares regression line. Now I can draw that. So I've plotted the points here. I want to draw a line through these dots that's reasonably going to fit. So I need to choose an x value that's somewhere on the left of my my data. So I don't know, 10. I could go a bit further. I could go 8. So that's the first point that I'm going to draw. So I need to find the distance when x is 8, 3.2895 times by 8 minus 20.3421. Do that in the calculator. 3.2895 times by 8 minus 20.3421. That tells me 5.9739. So my first point is at 8 and 5.973. So it's just going to be pretty much at 6. That's my first point of my line. 8, 5.9739 is my first point. I can't draw a line yet because that's only one point. So I need to substitute another point. And I'm going to do, let's do, I don't know, 21. So distance for when it's 21, 3.2895, lots of 21, minus 20.3421. 3.2895 times by 21 minus 20.3421, 48.7374. So the point is going to be 2148.7374. So let's plot that. 21 is up here. 48 is going to be like here somewhere. Okay. So now I have enough info. I have enough dots to draw my least squares regression line, or my line of best fit. That's more proper. There you go. That's a mathematical line of best fit. I do understand that 1, 2, 3, 4 on, and then 1, 2, 3, 4, 5, 6, 7 is slightly unbalanced, but I can't argue with this maths, okay? You've used a mathematical process to draw the line of best fit. So this is the preferred method unless you're running out of time, which is when you could use the drawing a line of best fit by eye. So now C, state and interpret the gradient of the least squares regression line. Let's write that down here. So you need to remember the question context. C, gradient was 3.2895. So that means for every year of age, distance thrown increases by 3.2895 meters. So now we're getting into interpretation of the gradient because we actually know it. We didn't know what the gradient was of the line of best fit. D, use the equation of the least squares regression line to estimate the distance thrown by a 14-year-old. So now this is what I meant by we hammer this particular topic, is because all the exam questions and the test questions go on. They don't just ask you to draw it. they ask you to use the equation. So I need to find the distance that a 14-year-old throws. So I know the x, and I need to find the y. So it's a simple substitution. Put 14 instead of x, 20.3421. So the distance is going to be 3.2895 times 14, and then minus 20.3421. The distance is going to be 25.7109, which is 14. It's around about there. So it's pretty good. It pretty much fits that line of best fit. Use the equation. Use the equation of the least squares regression line to estimate the age of a person who threw a distance of 60 meters. So this is slightly different. This is the hardest version of this. You know the distance this time. It's 60. I don't know x. So I'm going to put the equation in as far as I know. And then I need to use a bit more algebra than before to solve for age. So what is the opposite of taking 20.3421, adding it? So if I added 20.3421 on the other side, I'd have 80.3421 equals 3.2895 times by the age. If I added 20.3421 to this, there'd be nothing left. So the next step of algebra, what's the opposite of timesing by 3.2895? Dividing by it. So those are going to cancel. So age is going to be 80.3421 divided by 3.2895. 24.4238 to 4 decimal places. Around 24 years of age. Okay? Question F. So pretty much all questions in exams and tests are going to ask you to comment on the reliability of any predictions made. It's just a thing that I've noticed in SAFE, so I might as well get you to practice it. Comment on the reliability of the predictions made in D and E. This is always about interpolation and extrapolation. So in D, I predicted a 14-year-old. My lowest bit of data is a 10-year-old. So that's going to be an interpolation. But in question E, I think it was. Yeah, in question E, I was going for a distance of 60. The highest distance that I've got data for is 50. So that's going to be up here. That's going to be an extrapolation. So we've already spoken about the reliability of those things. So let's comment. F, D was an interpolation, and R squared is equal to 0.8414. And according to your textbook, I wish I'd had it open previously. 12 general maths, statistics, and also I need to write R because that's how we interpret the strength actually. 0.9173. So R squared was, was 0.91. A strong positive correlation So D was an interpolation, and R squared was 0.8414, so line was appropriate. And R was 0.9173, so according to your chart in your book, it was a strong positive correlation. So this was reliable. But E was an extrapolation. And the correlation was not extremely strong. And the extrapolation, can't even spell it, extrapolation was quite far from the data, (50 meters to 60 meters), so not reliable. Maybe it would be more reliable if it was closer. So maybe if the prediction we were making was for, I don't know, a 52 somewhere here, or 51, 52, maybe even 55. But this far out from the ages that we've got, considering the data that we have, and because the correlation is just strong, it's not extremely strong, you would say that it's not reliable. Okay, so that is a video on least squares regression line, or doing the line of best fit mathematically. Hopefully that helps you out, and I will see you on the next video.